And today I'm pleased to talk to you about Bixby. Bixby is a virtual assistant on the phone. And I'm going to talk about how we have built Bixby from scratch in Samsung, basically at Samsung R&D Bangalore. I take care of the voice intelligence R&D. And let me talk about that. So, intelligent assistants are, fast emerging, right? So as you know, 2000 was the era of the web, right? And in the 1990s was the era of the web. And in 2000, what happened is the mobile apps started taking over. And pretty much today, everybody uses mobile, right? So a lot of people are using mobiles, but that is changing fast as the devices, form factors are changing. So the devices are becoming more smaller and more ubiquitous. So you pretty much find devices all over. And things like AI speakers are becoming very popular. Just this year alone, the AI speaker, can anybody guess the number of users of AI speaker? Anybody? Take a guess. Huh? It's close, 47 million users. So in the US, there are 47 million users of AI speakers. So AI speakers are coming up in a big way. Cars are also becoming voice-enabled. So what we are seeing today is from the apps, the app world, we're getting into the appless world, where in the future, there's going to be no apps, and everything will run in the cloud. And you can access this intelligence from pretty much any device, and it'll all run seamlessly. So the human-computer interface has been evolving over time. And, the 80s was the era of the GUI, then the touch UI, and then the voice UI, and so on. So what we are seeing is that the voice assistant users are significantly increasing, as I said. And the other interesting thing is that the interface changes are leading the industry changes. So when the interface changes, soon after the industry changes. We launched Bixby last year. And in less than a year, there are 27 million users of Bixby. And what's unique about Bixby is that it is the first multimodal voice assistant. So let me explain you a little more about what is multimodal here. So Bixby lets you seamlessly switch between voice and touch modes. So unlike other assistants, which capture the whole screen, and there is limited functionality that they offer, Bixby offers you everything. You can pretty much go to any screen of the apps that are supported. And from there, you can speak, you can type, you can touch, you can do whatever. And pretty much every functionality that you can imagine is supported. We hope that this will make the adoption of voice even more. So as I mentioned, we launched it last year, and now it's available in more than 200 countries. English, variants of English, and Chinese and Korean are supported. We are working on more languages. And there are more than 75 domains supported. A domain being like a camera or a gallery or messages, that's a domain. And there are 27 million registered users, as I said. So let me just pause here, and I'll show you a small video on Bixby.
Meet Bixby. It really knows how to get things done. It knows what you want.
Hi, Bixby. Make this my profile picture.
Okay.
And what you don't want.
When I'm near the mall, remind me, no more shoes. Got it. I'll remind you.
It knows what you're seeing.
Oh, Bixby, screenshot this and text it to my hairdresser.
It even knows how to work all your apps.
Show me my photos of Gerald. Add the sunshine filter to this one.
Okay, here you go.
Add Rome to my bucket list note.
Order me an Uber to work.
Turn on flashlight.
Remind me to call Granny when I get home.
Got it.
Pull up the note called Mom's Cookie Recipe. Text Mom's sad face.
Turn on Do Not Disturb mode.
Create a new album called Nom Noms and add this picture.
Set a nap alarm for 30 minutes.
Oh, and Bixby, create an appointment on March 26 called Due Date.
A smarter way to use your phone. Bixby it.
So next I'm going to show you a live demo of Bixby. Just spare me for a minute. So you can see I'm mirroring my phone. And there we go. So there are a few scenarios of Bixby I'm going to try. Interesting, right? So I can invoke Bixby by pressing this button. So all our flagship phones and pretty much all the other phones that we have this small button here that you can invoke. It makes it very convenient, right? Take a screenshot.
Okay, I captured it. Let's check it out in gallery.
So your screenshot is in the gallery. Open gallery.
All right, I pulled
Screenshot is
up the
there.
gallery.
Create a collage with the latest 4 photos.
Let's edit it first, then tap or say save.
Share it on WhatsApp to John.
Let's send this message when you're ready.
Notice that I'm able to do everything just by using voice, right? I don't have to touch all those things. Makes it very simple, right? Open YouTube.
All right, here's the app.
Search for chicken biryani recipe. Scroll down. Play the second one.
Hi viewers, இன்னைக்கு homemade chicken biryani எப்படி பண்ண போறோம்ன்றத பார்க்க போறோம்.
Send a message to John, how are you?
Do you want to send a message? Say yes or no.
Yes. So notice how simple and easy it is getting, right? Now I can also do one more thing. I can set up some quick commands. So let's say there are many things I want to do and I want to make my life simple, so I can just create a quick command for it. So I created a command for getting ready for bed, right? Get me ready for bed.
Oh, sound mode is already set to vibrate. Done. I'd set an alarm for 21 hours, 28 minutes from now. Got it. Location is off now. You got it. All apps are closed.
So you can take anything in the phone and you can make a routine out of it. Okay? So some more things. Show the pictures I took today.
Sure. Here are 10 pictures.
Share this picture. Now notice that when I say
Let's
share
choose
this picture,
how you want to share it.
it brings all the various ways of sharing it. I'm not telling it how to share. I can pick anyone, right? And then do that. And I can also say, share this picture with, share this picture with David. Share this picture with David.
Okay, we can choose how to share it here.
When I choose how to share it, it sort of brings David on its own, right? It knows that it's David and it.
Do you want to send a message? Say yes or no.
And then I can also say, share this picture with David via WhatsApp. Okay, so it gets it. I can post this picture on Facebook. Let me try that. Post this picture on Facebook. So it gets it there, right? Okay, then just going along. So we support other content providers and service providers such as Uber, weather, etc. So let me show that. Is it going to rain today? I guess it doesn't know. So I mean, you turn on location and is it going to rain today?
Yes, Friday it will rain in Bangalore, with conditions reported as occasional showers possible.
Add a meeting with James for Friday at 2 p.m. Notice that I was on the chat bar.
Should I save this event for later?
Which is right back into this domain, right? Into the calendar domain and saves it. Right? And I can touch and I can do everything. Set swimming alarm for 5 a.m. every Monday, Wednesday, and Friday.
Sure thing. Your new alarm will go off into...
Show my missed calls. Shows
Done.
Missed calls.
You'll only see missed...
Book a ride to the airport. So it figures that out, right? So just going along, I think just a couple of more things. So yeah, I can make reminders. Remind me to call mom at 4 p.m. today.
All right, I've saved the reminder for you.
Remind me to buy milk when I reach home.
All right.
So things like that, I can do a lot of other things. And lastly, it can also rap for you. Rap for me.
Here's a little something I've been working on about my origins. See, a while ago, in a secret laboratory, on a dark, stormy night, Samsung engineered glory. Someone cried, it's a lie, and a switch was thrown. And the power of Bixby appeared in your phone. From photos to text, I'm your tech-savvy authority, connecting with voices, my singular priority. Talk, post, text, stream, everything on screen, here for every task. All you gotta do is ask.
Okay. So hopefully the demo was nice, and you can see this demo, outside. We have a stall outside, and we have set up a few demos of Bixby for you. So please feel free to go and see it. Okay, so just. There's some password here. Okay, so you just saw the demo. So let me explain you now how we did it, right? So basically, as I told you, and I even showed you, Bixby is very different from other voice agents. First thing, it supports every screen of the app. So no matter which app you are working on, it goes right there to the app flow. The entire app flow it supports. You can execute anything by voice or by touch. And it's context aware. So it's able to understand where you are in the journey, and you can mix touch and voice, etc. It affords cognitive tolerance, so which means that you can enter any command any way you like, and you can enter incomplete commands as well, and it'll all work. And then it's very frictionless. It works very, very simply, right? Even on the lock screen, it can work. And as I showed you, you can even automate many things in one shot. So this is an example of cognitive tolerance that I just demoed. So you can say, send this picture, you can enter the whole command or partial command and so on, and it all works. Right? So it basically understands the context. And we got some very good reviews, be it Forbes or CNET or Android. We got very good reviews compared to the competition. We have done much better. And all of this, I'm proud to say, was done out of our team here in Bangalore. So let me go a little more detail into the specifics of the NLU. Right? So I'm not going to talk about the speech recognition today, because that's another topic for another talk. That's also a very complex area. But today I'm going to focus on the NLU. So the speech recognition, which is ASR, converts the voice packet into a text, right? And the NLU takes the text input and then comes up with a command. The command can be executed on the phone, like you saw, or it can go to a content provider or service provider like Uber or WhatsApp, etc. Or weather, right? So here is the traditional NLU flow. So any NLU in the world has this flow, typically, right? So the first thing is to find out the domain. What is the right domain? So for example, when I say text to mom, the domain could be even WhatsApp, right? But it figures out based on my history, based on my preferences, and so on, that I like to use messages, right? So first is the messages, the domain classifier, right? It has to understand which domain you're in. Then the second is the intent classifier. It has to figure out the intent of what you're trying to do. What is the action you're trying to perform? And then finally, there's a slot tagger. So it understands the command and then extracts the parameters out of the command. So the slot is basically a parameter. So mom is a parameter, right? So what are the key challenges that we faced? The first thing is mixing of text and voice. First time in the world we did it, right? So there's a dual modality here. And then the massive input space. So we had supported about 75 domains, and each domain has lots of screens, right? And each screen, you can have lots of ways of configuring the screen, and there's all kinds of things. We had to represent all that, and then we had to manage that context, and so on. And then the other challenge we faced was the variable output space, which means that we have, Bixby is available in 200 countries. There are over 20, 25, 30 different models, and each model has so many variants and so many locales, and there are so many different carriers in other countries, US and Europe specifically. So there are so many types of devices we have to support. And the same command can work differently. For example, you say turn on tethering. Turn on tethering can mean USB tethering on one phone. It can mean Wi-Fi tethering on another phone, right? So the same command can mean different things. And same command can mean different things from different screens, as I'll talk about. For example, you say, find James. When you're in Contacts app, you're looking for a contact named James. When you're in the Gallery app, you're looking for a picture with contact James, right? A picture with James in it, basically. So this makes it very complicated, and therefore, we use deep learning successfully, and that was the only way we could have got this done. Right? And that too, you can imagine there are millions of users using around the world, right? So it has to all work in real time. And then the other complexity we had was of data. So we had lots of data, and we had to manage this data. So for any data scientist, this is a very interesting problem, right? How do you manage all this data, this complexity of data? And it's very important because, unless you manage the data, you cannot do this project. This is impossible to do without the sanity and the diligence and all all the infrastructure, the process that we had around data. And the hardest part of this project was domain classification. So understanding the right domain, every screen, figuring out what the user wants to do. So for example, if you're in YouTube, you say search for Michael Jackson, it knows it has to search in YouTube. But if you're on the home screen, you say search for Michael Jackson, it'll probably go to the internet. Similarly, if you say, show me the price of S8 Plus. Now that means you're referring to S8 Plus phone, right? And that means you have to go to the internet or somewhere, right, to get it, or maybe a Amazon or Flipkart site to get it, right? But it shouldn't go to the calculator. What was happening initially is the S8 Plus, because of 8 Plus, that utterance is going to the calculator domain, and so on. So there are many examples of that. Another example is remind me to send a message to John. So that should go to the reminder domain and not the messaging domain, right? So such like things, we had to maintain a lot of balancing of the data, and we had to handle some rejection data. So I'll explain this more later. So I'll just explain the flow a little bit. So as I told you, so this is the multimodal interface, and as I showed you, with one utterance, pretty much you can execute the entire flow, right? And as I also told you, find James in the contacts application can mean contact information of James. Find James in the gallery application means images tagged as James, right? So it's different. So you have to understand the context. So therefore, you have to build a context-aware NLU. So we did that, and we had to manage this massive number of contexts and this massive number of commands, because there is, as I told you, various device models, apps, locales, etc. So there are about 2,000 contexts, and there are about 6,000 commands that we support. So 2,000 contexts, meaning the 75 apps, we have 2,000 different screens, and there are 6,000 commands that we support. So what we could have done is we could have built a classifier for each one of the contexts. But that is not a very efficient way to do this, because that would have meant crazy amount of computation and maintenance, etc. So we couldn't just do that. We had to build one classifier. Right? So therefore, we used deep learning, and we did build one classifier. So because of the massive amount of data, we had to use deep learning. We couldn't use anything else. So as I mentioned, we had about 75 domains. Mentioned 60 here, but actually it was 75. Increased later. And we had 6,000 intents. And we had about 10 million data for domain classification and about 1.5 million data per intent classification. Right? So roughly, this is the kind of data we had. And deep learning came to the rescue, and we did that. So basically, what we built is a context-conditioned DNN classifier. And also, what we had to do to build the classifier, we had to sample the data, because we could not train all of the data for the classifier. So we had to sample it, and we had to sample it in a very intelligent way and very carefully controlled way. Right? And also, what we built is a hierarchical classifier. So for example, when you say call a taxi can be a sort of a meta domain, and you can have Uber, Ola, etc., various providers. Similarly, we had something where we could figure out if the utterance is a chat utterance or not. So we had something called a pre-chat bot. So you can figure out whether it's a chat utterance and take you right there. So it's like a hierarchical classifier in place. And also what we had is a session-based architecture. So for example, if you're on YouTube and you say search for Michael Jackson, it first looks in the current domain, because that's the session. But let's say you say, what's the temperature now? It kind of jumps out of the session. So we had to train the sessions with rejection data. So when to accept utterances and when to reject utterances. So we had to build the rejection logic in the intent classifier. And many times the domain classifier mispredicts, for example. So we had to make sure that the intent classifier can reject it, right? So that required data as well. So all the data that we used had to be very, very carefully managed. So next I'm going to go into the techniques we used. So typically in text, RNNs are used, right? Typically. But recently there's been a lot of literature talking about the use of CNNs for text. So we experimented with both. Initially we were using RNNs, but RNNs had the issue that they were not learning unknown words. So for example, you mistype some words, or misspell some words, or even many users speak differently, right? So there could be unknowns, and with those unknowns, the RNNs were not working. And the other thing was the state. So we used word-to-vector embedding, which had about 300 dimensionality, but the state dimensionality was very less. It was like just 1 or 2, dimensionality. So the state was getting lost in this embedding. And therefore, the RNNs were not able to learn the state very well. And because of that, we were getting random jumps all over the place. It wasn't working very well. So we switched to the CNN character model. And what we found is the CNN character model worked very well for us. And ultimately, we ended up using that for the domain classifier and the intent classifier. For the slot tagger, we still used the RNN model. So with CNNs, again, we used the typical, deep net architecture. And we used layers, different layers, series of layers, convolution layers, pooling layers, and so on. And finally, there was a fully connected layer towards the end, and then the output layer. And then we used different types of filter sizes. So we found that smaller filter sizes worked very well for sub-word level features. Larger filter sizes worked well for understanding language structures. So we used many filter sizes in parallel, and then finally, with a fully connected layer kind of decides which goes, right? So we used dropouts as well, and we also experimented with attention. So these are all the things that we try to use, and we keep improving this architecture as we go along, right? So I mentioned about the variable output space. As I told you, the same command turn on tethering can mean different things in different devices. And we didn't want to overload the NLU with this information. So because the NLU is as it is complex enough. So what we did is kind of abstract that out from the NLU. And we had a version DB with version mask vectors. And we had sort of metadata and stuff like that. And so we could sort of come up with a version mask vector. And based on the version mask vector, we could actually generate the right command. So this was very successful and helped us manage the complexities. I told you there are so many different types of devices that we had to deal with. So the key learnings in the design was that we had to experiment with various DNN architectures. So any data scientist, should experiment, right? Don't just go with the traditional approach. And the obvious choice may not work the best, right? And hierarchical design could work very well for you. And also, we experimented with rule-based matching of the NER versus a machine learning-based matching of the NER. So what we did is, in our case, the NER had to be very precise. For example, you say play a Summer of 69 as a song. It has to recognize Summer of 69. But if you say play Summer of 696, obviously that should not work. So we had to use a rule-based NER as opposed to a machine learning-based NER. And then, as I told you, we had to use a rejection-based intent classification and so on. So I talked about data. So in this, we had a lot of data. We generated data synthetically. We had data that, was sort of quick grammar data based on some rules. We created some data. We purchased a lot of data. We had a lot of language generating data for us. We had crawl data. And we had voice of customer data. That's actual data that we got from live customers. All of this data we had to manage very carefully. For the domain classifier, we had to sample the data. We sample about 2K per class. And for the intent classifier, we sample about 10K to 20K per class, and so on. And we had to clean a lot of data. So this is a massive amount of data flow that happened, right? And we had to use some governance in this. So we had to figure out where data is conflicting. We use tools like TF-IDF to figure out whether the data that is being trained is representative of the domain or not. So TF-IDF tells you which are the most commonly used keywords occurring in the domain, right? So it sort of makes you, sort of guides you whether the data you're feeding in is representative or not. Also, cosine similarity can help you decide whether two word vectors, how close they are to each other. And if you have very close word vectors in two different domains, obviously it means that there can be a problem, right? Tomorrow, if the similar utterance comes, the DC can get confused, domain classifier can get confused. So we use tools like this, and we are continuously evolving these tools. So all in all, we had to have a governance around data. We had to have, process around data, and we had to have various test data, and validation data, test data, training data, all had to be separated. And, we had to, basically, the traditional software development lifecycle doesn't work here. You need to have a very different kind of mindset and different kind of lifecycle for data. And roughly, we have about 30% of our data scientists, 30% of the engineers were looking at data, purely on data, not about training, not about algorithms. They were just looking at data. And we had teams whose only job was data. So data is all about data. Finally, at the end of the day, to improve your system, to make your system flawless, it's all about data. Algorithm is important, but data, I feel, is more important. So the key learning is that managing the distribution and the variations of data is essential. Quality of data is essential. Balance of data is very important. Special handling of rejection data was very important for our case. And a deep learning engineer, data scientist must spend 30% of the time looking at data. And as I told you, people are needed to manage this data. And tools and automation are needed to manage this data. And hand cleaning or hand engineering of data is not, you cannot avoid it. You need to do that, even though you want to minimize it. And these days, there's a lot of work on automating some of that. There's a lot of work on one-shot learning, zero-shot learning, reusing transfer learning. There's a lot of things happening, and we can sort of minimize this active learning and so on. So they can minimize this, but still you need to manage data and so on. So these are the key learnings. So that's all for today, and I'm open to questions. Thank you.
Hello. We have time for at least 2 or 3 questions. I'll take the first question from here.
Sir, you said it works on the lock screen too.
Works on?
It works on the lock screen too?
Yes. Yes.
So what if it recognizes someone else's voice? Does it recognize recognize and respond to the owner's own voice or someone else's too?
We trained it so that it can recognize only the owner's voice.
Yeah. Okay. Thank you, sir.
Slide, you have mentioned crawl data out of domain. What do you mean by crawl data? And this device is compatible with Samsung devices only, or is it compatible with other devices also?
No, this is Samsung devices only, and precisely we are launched only on Samsung flagship phones, but we have a plan to spread it to other devices. So we have a plan to actually open this up to other devices. At the moment, it's only Samsung devices, but soon we're going to be opening this up to all other devices as well. Okay. And you mentioned about crawl data. So crawl data is basically crawling the web for data, right? So, and we sometimes have to gather the data from the web because there's so much of data, right? We have to get that, especially for things like acoustic modeling. We need to have data, a lot of data that we have to gather from the internet.
So just one question. So by looking at the demo, it seems like you are imitating user input, as to say.
You're what?
So by looking at the demo, it seems like you are means the Bixby was imitating the user input, like go to the options, open WhatsApp, and then search.
Yes.
Yeah. So means so you are using it by the going to the options or looking at what's on the screen, as to say, means like capturing the screen, what's on there, and then analyzing and based on that selecting the input.
No, it's just mimicking your flow. So if you were to touch and do the thing, what you were to touch and do, right? It will do using voice. That's it.
So means so for that you are using means what's on the screen, what options are present on the screen, and then using it, or
yes. What's on the screen? Maybe I have Siddharth here, one of our key architects. Maybe you can explain more. Just wait for the mic.
So as Vikram mentioned, that we have a massive output space. For that, we have a knowledge base. You could have seen in one of the slides, it was mentioned that Tab, Galaxy S8, so different devices with respect to different app versions, with respect to different launch and different operators, we have these flows. So after the deep learning, when it predicts, we have a separate knowledge base or ontology that mimics what's supposed to happen for this phone. So entire phones, whatever the screens, all the 75 apps which we support, their entire screen flow with respect to the app version, with respect to the device version, those knowledge base are there in So once NLU predicts, the entire prediction goes to that server, then the knowledge base actually filters and modifies the output, then it goes back to the actual device. So after that, finally another NLG comes back and TTS servers comes back. So that's a separate flow altogether. That is not part of this today's.
Hello. Hi, Dr. Vikram. So I have a question that, I mean, somewhere towards the end, you mentioned that we are also using synthetic data for training it.
Yes.
Right? Yes. So my question is, when we train using a synthetic data, the NLU engine will learn the reverse of the process which was used to generate the data, right? So instead of, why not use the generation data and infuse that into your learning model?
Okay,
I mean, if you already know algorithm, how you can generate data and train a model on it, it will learn the process of how that data was generated, right?
Yes, but I think it's an interesting problem. Siddharth, you can answer.
So it's an interesting question. Yes, traditionally, this is one of the another key learning. The traditionally deep learning system understands what the generic data. But to be very honest, to target this space where we have 6,000 intents across 200 contexts, so it builds us a massive context space. So there is no available data as such which you can support. So 1.5 years back, so the first target was create a team of linguists who can generate data, whatever the possible way you can create. So now synthetically generated data does not mean that we have handcrafted only the utterances. The things what we did, we had an open specification, some of you might be knowing, JSGF grammar format. So it's basically that automata is a context flow grammar. So based on that flow, we have created grammars through a script which can automatically generate all the variations for single intent. So that's how the primary models are getting built. After that, when the first level of models are built, we will have some decent amount of accuracy you put into productions. The moment you put into productions, you will start getting actual users' data. Then you start mixing it. That's why such a complicated data flow was there.
Okay.
Even after synthetic data, there are some cases where you cannot handle the problem of determinism. There are some cases when the user is telling call 911, you cannot afford to miss whether you are using deep learning or whatever. In that case, we have a specified learning that Dr. Vikram has already showed that there is something called quick grammar. So quick grammar was to handle directly that data in a string matching format, almost, not exactly string matching, but almost, you can think of that way. So the data flow, this is the data flow. So that's how all these variations were used. So as I said, the domain classification, 10 million data for in-domain. Crawl data, somebody has asked, that is for the out-domain data. So that we need to collect, not only for the out-domain, there are other cases. For example, all the possible cities for the weather, when I have to support, we need to crawl. Different types of cities, different types of name, different types of ways the cities are represented. That's why crawl data is in there in the picture. Yes. So majorly synthetic data was for the purpose when I had to create the first level of classifier input where it can understand all the possible ways of saying 6,000 intents across 2,000 states.
Hi, we have crossed the time.
Like
We'll take one last question and then the rest of the questions.
And what kind of effort does it take to scale to a new domain or to a new app? Like a week, a month?
Can you repeat the question?
What kind of effort and time does it take to scale up to a new app or a new domain?
Sure. So what we found is typically for every new domain, it took about 3 months, right? Around 3 months, and maybe a team of like 5 engineers, 5 or max 10, depending on the domain. I mean, the domain can be simple or complex. So 5 to 10 in 3 months. But we are working towards reducing this. And in the next version of Bixby, we are going to open it up more, and because we ultimately want to have thousands of domains, right? So we are working on that, and I think soon you should hear about it.
Okay. Considering the time crunch, we'll take one last question, and the remaining questions you can
ask. On the grammar, I just want to comment one thing. So as Siddharth mentioned, we took the grammar, we generalized. So based on the current data, we kind of made a grammar. And using that grammar, we were able to generate the data, because generating all the data manually is impossible, right?
Sir, you mentioned that you have used rule-based grammar to identifying whether proper searchable text is accepted or not. So what are the alternatives you have gone through before finalizing the rule-based? For example, there is SMT and like that.
So exactly what you, just to rephrasing your question, you mean to say whether we have evaluated any other rule-based system?
Yes.
Yeah, so this is not a single rule-based system, first of all. So there are various hierarchy of rule-based systems we have. So as per the overall flow, which we cannot expose here due to the constraint of the licensing and all, we have a chatbot even before that at the end of the system. So first level of chatbot is a rule-based chatbot which has to support some of the basic things for a business need. Then comes the other rule-based systems. There are various rule-based systems, even some of the quick grammar sort of thing that has different layers. So inside that also have a different types of rule-based system. Some rule-based systems are based on semantic pattern match. Some are based on the variation match. Now, what to evaluate? Before Bixby comes into the picture, we had our system called S-Voice. 3 years back, it had been commercialized, it was there. So there we had a very strong rule-based system. That rule-based system is used as a part of the rule-based system, whatever has been claimed here. So that rule-based system has a lot of other intricacies and a lot of other things. For example, when you show that RNN layer, the slot tagger, is tagging a time. Now to understand the device-specific time, it has to convert into a proper time format. I said day after tomorrow. So day after tomorrow has to be interpreted in an Android phone language or a Tizen device language. That is done by that kind of spaces. And we have our inbuilt system, in-house system, some few lakhs of lines of C++ code for the rule-based system. So I cannot tell in very small time. It's a very big system. Yeah, we have an inbuilt in-house system that we use.
Yeah, we launched S-Voice about 4 years back. So, you know, this Bixby was only last year, right? So it's a kind of evolution.
In the interest of time, we request you to take these questions to the Bixby booth. Dr. Vikram is here.
One more thing. So one is the Bixby booth we have, and second thing is we have a birds of feather at around 4, right? So that's around data. So you can join that too.
Thank you.
Thank you.